Welcome PCS members and friends to our today's PCS IBS seminar. It is a great pleasure to have with us today Professor Dario Poletti from Singapore University for Technology and Design. And I would like to invite our scientific host, Dario, to introduce our speaker. Please, Dario.
Yes, thanks, Dylan. It's a great pleasure to have another Dario Poletti with us today from Singapore. So let me introduce a little bit his career. So Dario got his PhD in 2009 from National University of Singapore and Australian National University. And at that time, he was working on quantum ratchets in Bose-Einstein condensate. And then he moved, he remained in Singapore for a while. He moved to the Center for Quantum Technology in Singapore. Then he has been also in École Polytechnique, University de Genève, also CNRS. And finally, from 2012, he is back to Singapore, again in the University of Technology and Design, where he is now an associate professor. He is working on several topics on quantum physics, quantum machine learning, quantum nanodevices, and so on. Topics that we are also, working on here in IBS. And today's talk is about tensor networks for classical and quantum machine learning tasks. Dario, I think you can start.
Hi, thank you, Dario. Thanks for having me here for this presentation. Some familiar faces. I've been to the IBS a few years ago when it was in the previous location, and I'm glad I will be visiting in 1 month's time during the dynamic days. So see you in 1 month's time for those who are there. Yes, today I wanted to tell you a little story about using tensor networks for machine learning tasks, both on some classical and quantum, classical quantum tasks. And okay, good. So this is the outline. I will give an introduction to some aspects of machine learning which are relevant for the talk, and then on tensor networks, so that those of you who are not familiar with tensor networks can get an idea of especially the graphical representations that I will use later on in the talk. And then I will go into our results on matrix products operators for sequence-to-sequence learning, and I will explain the method, and then show application to classical cellular automata dynamics, some diffusion, and then also application to understand dynamics of generic quantum processes. Okay, and then some conclusions. So this is the plan. Feel free to ask questions during the presentation. Okay, so I will start with the introduction. And for machine learning, there are 4 main different categories, depending on whether you have in mind a classical application or a quantum application, or whether you're using a classical hardware and classical algorithms or a quantum hardware and quantum algorithms. So these are the 4 main paradigms. You can also find these in, for example, Cellular review. And what we are talking about today is using classical hardware and classical algorithms throughout, although the algorithms that we use may fall into this category that called quantum inspired, because we use an algorithm that was first developed to tackle quantum problems, which is tensor networks. But the applications will be both classical and quantum. Now, my background since just after the PhD, let's say, is many-body physics, as Dario Rosa was mentioning just now, and so my approach towards this topic is really from a many-body quantum physics perspective. And there has already been several links between machine learning and quantum many-body physics in different directions. And I would just like to mention a few, which are particularly relevant for what I do typically, but may interest many of you. And one, for example, is to use machine learning, for example, to detect phases of matter. And these are things that have been developed long ago, also by Eunhan Kim in Cornell and so on and so forth. Then there are interesting works on interpreting machine learning using the tools of physics. And in this direction, there are various nice works in this direction by Benny, Mehta, and Schwab, or Max Tegmark and other people. And what I'm interested in, and what I'll talk about more today, is about novel algorithms. And here there has been a number of works, and I think the first one is this one that I highlight here in 2016 by my student Meyer and Schwab, where they use a tensor network to solve some classical machine learning task. In the specific case was a task of classification. They were just trying to understand manuscript numbers, the classical NIST problem. And later on, this was for the study by Pan Zhang and others, Lei Wang and so on. And actually, if looking a bit more in the theory, in the literature, you can find the works by Novikov, Trofimov, and also that's who are, from my understanding, computer scientists. They were trying to do using something that they were calling exponential machines, which are basically tensor networks, for some mood detection tasks in machine learning. So there has been quite already a number of prominent links between machine learning and many-body physics. Not to talk about also neural network quantum states developed by Carleo and Troyer in 2017 in Science, or even using neural networks to accelerate codes for quantum Monte Carlo or so on and so forth. So there is a lot of interest and research in these directions. Now, what I'm going to use today is tensor networks, and here already we see some graphical representation that people who are familiar with tensor networks will straight away recognize, but I would like to introduce to you a little bit more this for those of you who didn't have the pleasure to work on tensor networks. So let's say I have a many-body system which with local degrees of freedom that I can describe like sigma 1, sigma 2, all the way to sigma n. I can write a wave function, which is basically a superposition of all these basic states. And so I will need all these coefficients here, C, sigma 1, sigma n. And now, of course, the number of these coefficients goes as d to the L, where L is the number of local positions, and d is the size of the local hyperspace. And this obviously is a very big problem, because it scales exponentially, the size of C scales exponentially with the system size. The point is that one can decide to write this coefficient, each of these coefficients, as a product of tensors. And while this may seem like an overkill, because now instead of having one number, you have a product of many tensors, this actually has a great advantage, because while in principle the size of this tensor should also grow exponentially with the system size, in practice one can try to one can bound the size of these matrices to something which called bond dimension capital D. And then it turns out that in many systems, it's sufficient to describe extremely accurately the system. And there are a number of theorems and numerical descriptions of when that, for example, for 1D gap systems with local Hamiltonian, it is entanglement is bounded, and you can describe these systems very, very well. There are these area law theorems, and even for critical systems, entanglement will grow in 1D only logarithmically. So it's also they also can be described efficiently with tensor networks. Of course, people try to use them beyond, also in regimes where maybe you can have also volume laws, and then you will be able to only study finite size system or system only for a finite amount of times. But in 1D, what happened is this method is really like the best method I'm aware of to study quantum systems. When we go to 2D, things maybe become more complicated. Now, as I said, I wanted to give you in a graphic how we introduced you to how we describe graphically these tensors. And this is what we do. For example, if I have coefficient sigma 1 all the way to sigma L, I can describe it as many vertical indices which represent physical indices, and then the horizontal lines represent auxiliary indices. Okay, and when I write something like this here, it means that it implies that there is a summation over these indices which are touching. So in this case, on these auxiliary indices. Now, once you describe a state with this object, which we call a matrix product state, we can also describe operators with this slightly larger object, MPO, a matrix product operator. And here, instead of having as a core element a 3-leg tensor, as we have 4 states, we have a 4-leg tensor with 2 physical indices, sigma I prime, and 2 auxiliary indices, beta I minus 1, beta I. And then, of course, you can multiply an MPO with an MPS, and this will result in another MPS, and this is how we will represent it, okay? And obviously the bond dimension, so the number of indices you keep here may increase as you do this, but sometimes, this can be contracted and things can still can be described in a manageable way. Okay, so this MPO times MPS is something that I would like you to keep in mind because we will use it later on quite a bit. Okay.
Yes. Professor Poletti, we have a question from Sungjong.
Yes.
Sungjong, please unmute yourself.
Now, I have very basic and naive question. Like, if I multiply all those tensors, then it basically becomes 2x2 matrix, right? Each term becomes 2x2 matrix. Does it have anything to do with like spin half system, or
where does it become a 2x2 matrix?
Like, that so like the rank of tensor is 2, right?
Okay, so let's say sigma 1 is as dimension 2, then this whole object here is 2 to the 5, okay? So yes, 5 legs is legs as dimension 2. So the overall dimension of this object here would be 32. Because each open leg is dimension 2, right? And then you have tensor product between them.
In the first line of this page, like the matrix multiplication, the tensor multiplication looks like the indexes goes from A1, A2, and A2, A3, and A3, A4. So I guess it's gonna be all those A2, A3, all those like intermediate indices is gonna be contracted, and the only index left is A1 and AL plus 1, isn't it?
Yes. And actually, well, no, yes and no. So the A1 and the L plus 1 will remain. And this is in open boundary condition scenarios, these are dimension 1, so they don't matter. The only things that remains is the sigma 1, sigma 2, sigma L. So which is this thing here? You see?
Oh, okay. Okay, I see. Okay, yeah, thank you.
Okay, good. Okay, I shall continue. Now I would like to describe the algorithm based on MPOs for sequence-to-sequence learning. And to do this, okay, the way we were really inspired by the works of Stadelmeier and Schwab, where they were using tensor networks to do classification. And we were discussing with some people here in my university, CTD, who work on natural language processing. And for them, the task is not so much classification, but it's like sequence-to-sequence prediction. And so we will say, okay, can we given it, and this problem is like this: you have an input sequence, and you have a function of this input sequence which gives another output sequence. Okay, so you can go from like a vector like this to another vector, or a more complicated object than that. And so we try to see, okay, a function of this type, can I describe a function of this type with a matrix product operator. So if I have my first sequence, I describe it as an MPS. I can encode the sequence in an MPS. Can I find the MPO such that this MPS times the MPO gives me the correct output sequence here? Okay. So this is what we wanted to do. And obviously, there may be cases in which it doesn't work, but maybe there are cases in which it works. And so we try to play with it. So how did we do it? How does the algorithm work? So we take a sequence of inputs. This is here on the left, I show the training portion and then the testing or prediction portions. Okay, I take input sequence and output sequence. I convert each one of them in an MPS. And in this case, actually can be converted in a trivial MPS with bond dimension 1, if I take one sequence at a time. One extension would be, for example, to take more sequences at the same time and make an input MPS of larger bond dimensions, but we haven't done that. So we take this and then we train an MPO. Later, I'll show you how we train the MPO. And then what we want to do is, let's say, in the testing phase or in the prediction phase, we take a sequence, convert it to MPS, multiply by the MPO, obtain another MPS, convert this MPS into the output sequence, and this will be our prediction. Okay, so this is the main idea. Now, how do we do the first step of converting input data into a sequence? And then, okay, here, okay, this is already described. The input data, if it is just a sequence of zeros and ones, okay, locally, for example, or if I have a local Hilbert space and this can take only value zeros and ones, then I can use two vectors, one hot vectors of size 2. If this is a real number, I can still use a vector of size 2 and then use an angle, cos theta, sin theta, and do encoding in this form. Now, how do you do the training though? Well, basically, I need to build a cost function. Okay, it's a very simple thing, and this is a least square mean error, where I have the exact data output here, and then the predicted data, and I do the difference and the square of the differences. Okay, and sum over all the input data that I have, all our training data, and so this gives the square error, mean square error. But then I also add a regularization term, and this is important. For weeks we didn't have this term, and our system was always overfitting, and the predictions were really poor. But if we have put a regularization term, which try to minimize basically then the values that you get in our MPO, then the performance are significantly better. Okay, once you do this, we can do a local minimization of this loss function. And basically, as we do for DMLG calculations, where you try to optimize one by one and sequentially different local tensors, here in the same way, we try to minimize to find the minimum of the cost function locally for certain tensors, and then move to another tensor. Every time, this problem at each iteration, this problem is just a linear problem to solve, and we can solve it fairly accurate and fairly fast. And then we sweep through, and we minimize the cost function like that. So when we have done this, then we need to go for prediction. Again, we have converted the data into a sequence, multiply by the MPO, you get an MPS, and then convert this MPS to data. Now, how do we do this? The one way to do it is to find the MPS at bond dimension 1, which is closest to this MPS that we have produced, which is typically bond dimension larger than 1. Okay, and once we have done this, we are back to a series of MPS, which you can easily convert to a set of data and our sequence. And so this is how we do the prediction. Okay, so now let me try to move towards the application. The first application we thought about was cellular automata for various reasons. One, because the rules are fairly simple, but the dynamics can be very complex. And two, also because the local values can simply be 0 or 1. So we thought this was an easy place to start. And also already in one dimension, it's fairly rich. So here I give you an example of the evolution of a cellular automata here with rule 30, which for a particular initial conditions. And for this particular condition where everything is 0 and this value is 1, it evolves this way. Now, interestingly, it is possible for all the 256 rules that you find from the, from Wolfram's review, for example, to write exact evolution, exact solution with MPS. So we can write MPOs that describe exactly the evolution. For example, these MPOs in the center of the chain will represent exactly rule number 30. And actually, all of these rules can be written analytically, exactly, with a bond dimension at most, which is the size of this matrix, at most 4. Okay, 4 by 4. And actually, for many can be compressed, and some can be written easily with bond dimensions too. So actually, we know that these setups can be described exactly with MPOs. So it's an ideal place where to check whether our learning algorithms work, because in case it fails in this place where there are analytical solutions in MPO form, then we are doomed. And in case so here it should work, and so we tried it here.
Professor Poletti, we have a question from Dung. Please, Dung, go ahead.
I have a question. So in my impression, the way that you're doing now is very similar to the neural network, but with a new kind of loss function, I think.
Yeah, more than the loss function is the network that is different. Instead of using a nonlinear network, we're using a linear network, basically, and which is built on tensor networks. Now the question is,
at the moment it looks very similar with the neural network. Is that the way you define the loss function different? Rather than that, I think it's almost the same.
It's not very different. In many places, the loss function is defined with this least square mean square error. Okay, and adding a regularization is not too unorthodox either. Okay, so I wouldn't say there is particular novelty here. Now the question is the novelty or the different thing is really to use this specific linear network made of tensor networks as what we use to learn. And now you could ask why to do this. Now later I will show you comparisons that for some problems that we do, this performs better than some state-of-the-art, or at least at that time when we do this work, state-of-the-art techniques. The other one is that certain problems are, some of the problems that we discuss here are naturally described by MPOs. So it seems like MPO it could be the most suitable network to use to learn that dynamics. And this one is one of them, because here we know that the dynamics is exactly represented by MPOs. Okay.
So maybe the improvement is that you can use quantum to simulate this kind of learning with the quantum hardware, I think.
Well, now I'm only describing classical tensor networks. There are extensions to do this on quantum hardware as well with quantum tensor networks, but this is not what I'm going to discuss today. But already at this scale, there are advantages of using MPOs instead of neural networks for this dynamics, and I will show you some advantages later on as we continue.
Okay, thank you.
Okay. So now these rules, as I said, can be described easily by simply by 4x4 matrices. So we use extended the rules to, for example, rules where the color or the value that a cell takes at a certain times does not only depend on the nearest neighbor, but also from sites which are a bit further away at the distance j. Okay, and so in this case, for example, rule 153 with something at distance j will need to be exactly described at dimension of 2 to the j. Okay, so this is what we use. Now, how do we train it? We prepare a set of random random sequences, zeros and ones, and these ones are completely uncorrelated one with the other. And we have the input data and the output data. The output data is line by line correlated to the input, but between each other they're uncorrelated because these ones are also uncorrelated. And we train them with this rule 153 at a distance j. And then we try to do the prediction, and we see that the predicted one and the exact evolution are perfect. And indeed, as soon as we hit the mode dimension that is large enough, we can do perfect predictions of the dynamics. And okay, this seems maybe a bit easy because the dynamics is periodic with a very small period. But if we take one of those chaotic rules like rule 18 and a much larger system like 60 sites, we can evolve up to 500 time steps, and you can see that the dynamics is highly non-periodic. And the predictions that we have from our MPO algorithms are perfect without any error, because locally it's find out what is the right MPO, and so then it can predict the dynamics for indefinite amount of time. Okay, so this was in a sense a scenario in which we expect this to work, because we know that the solution can be written as MPOs. But we can also look at scenarios in which there is no exact solution. And for example, we look at this strange nonlinear equation, where we have some longer range coupling, nearest neighbor coupling, some nonlinear terms, and just cook a bit things together and see whether we can predict this. So what we do is similar to before. We train it by taking some random numbers on different sites between 0 and 1, and the corresponding output at the next time step. And we train this with thousands of different initial conditions. And then we choose 100 initial conditions which are smooth and a bit oscillatory, like a cosine times a Gaussian. And then we see whether we could evolve this accurately. Okay, so to give an example, this is an example of 30 input data, which are uncorrelated along this direction. And on each side, you just have a different number between 0 and 1, randomly chosen. And then this is the corresponding output. And we use this to train our system. And then we take these different initial conditions. Here, there are 3 examples. And you can see on the left the prediction, and on the right, the exact value. And we can see already by eye that it seems to work pretty well. Here we used like 20,000 different initial conditions for training, and an MPO with bond dimension 20 and a system of size 20. To be more quantitative on the performance, we can look at the error, okay, on each site as a function of the bond dimension that we use, and we can see that the error can be significantly below 1%, or as a function of the training data. And as we increase the training data, this error can go down significantly, okay, even like 5 per 1,000. And also of this regularization term, and we can see that if the regularization term is small, but not too small, where it goes to overfitting like this, we can get very, very good performance. Now, both of these, the previous work and this work, were benchmarked with state-of-the-art algorithms. For the previous case, we used the conditional random fields. And conditional random fields also can predict exactly the evolution, but it needs to know which features to take into account. So basically, we need to know which sites are coupled for it to work very well. While the MPO system As long as you have large dimension, large enough bond dimension, it will be able to describe the system evolution correctly without too much information. Now, in this case here, we were using a we were comparing with a bidirectional recurrent neural network with LSTM cells. And this setup, despite taking significantly longer time on many more cores and GPUs, it was taking much longer than our algorithm to produce performance which are slightly worse. So it seems that for this scenario and the other one that we studied before, these algorithms can be better than some neural networks that have been used. For other, we tried also for some tasks like natural language processing, and in this case, we tried some couple nonlinear maps which are highly chaotic, and in those cases, the performance of the MPO algorithm were not very good. But here, there is definitely a class of problems in which they're very good. And now I would like to give you, in the last, about 15 minutes or 20, whatever is needed. I would like to give you a specific example of an application which is, by design, we expect to be very well represented by the MPO. And so learning with an MPO, it would be particularly ideal. Okay, this application is to learn about some quantum processes. Okay, so let's say we take a quantum system S, and we would like to understand how it performs when it is within an environment. But not only the system and the environment, we want to do things on the system. We want to do preparations, we want to do measurements, we want to do unitaries on the system. And whenever you do a preparation on the system or a measurement on the system, it will affect the environment as well, because the system is coupled to the environment. And this can feed back later on, at later times, on the system itself. Or when you do a unitaries on the system, it will still affect the environment, and it can, if the environment has some memory, return some of this, can feed back into the system and affect how the unitaries that we do at a later time, how they will affect the system itself. So it's very important to try to understand, for example, from a sequence of unitaries that you do in the system, what would be the final output. And to do this, we need to learn how the setup system plus environment act together. Okay, so let me try to explain this a little bit with a few more steps. I have a system. I can do some measurements and preparations at one time or later times. I can model this in this way. I have a system there on my site 0, and I have an environment which here I can describe with a finite set finite number of sites, but of course can be infinite. And we can talk about this more later. It's not an issue. But just to have a pictorial view of what's going on. Then we have an evolution of both system and environment together because they're coupled. Later, we can do something on the system. And whenever we act, let's say we want to do some unitaries or some measurements and preparations, something, we will try to act on the system, and the assumptions that we make here is that we do this fast enough that the environment is not evolving in meantime, and effects of the coupling between the system and environment are not acting during that period. So this is an assumption that we do. And then we can do this many different time steps, and in the end, do some measurement on our system and figure out, try to see what happens. All of these things, okay, is what it's called in the literature as process tensors. The only thing that are not included in process tensors is the system at the beginning and whatever operations you do on the system, but everything else comes out and it can be put together, and you can see it becomes like a tensor with some extra legs. Let me try to describe this tensor a little bit better. I have the setup that I described to you just now. Okay, and then I remove the system and the things I do on the system. And I'm left with something with some extra legs, okay? And these extra legs, I can reshape them as I want. With this direction will be different time steps. And I'm left with an MPO. And that's why it's also called a process tensor. And you can see this is the natural representation of all of these dynamics is indeed an MPO. And what I described just now is how to learn MPOs. So maybe this is what we want to do. We want to try to learn this MPO. Now, how complex is this process tensor? Now, naively, you can think that the complexity grows exponentially with time. Because at different time steps, at every time steps, there is a certain number, for example, of unitaries that you can apply, and then the next time there is multiplied by the same amount, and so on and so forth. But in reality, this complexity may not grow exponentially with time for two main reasons. One, which in some setups, okay, the size of the buff could be finite, or the relevant size of the buff could be finite. The other one is that the buff could have a short memory, and if it's a short memory, whatever happened at times beyond certain times in the past would be there will be not much information carried from times very far away in the past, and so the amount of memory is basically can be large, but it can be finite, okay, and it doesn't have to grow exponentially with time. And in these scenarios, then it would be really manageable, not just possible to write it with an MPO, but also manageable. It would be also effective, it would be also efficient. Okay, so to simulate this, we had an equivalent circuit model that helps us to generate the data that we needed to describe this thing. And so, for example, we have a set of preparations, okay, and then a set of measurements, and then we do a preparation, we put it in, evolves with the environment, and then we do a swap with another preparation, and continue swaps with other preparations, and after that we do measurements. And you can see then we have a sequence of input preparations and sequence of measurements. And then the last one is the final result, the reduced symmetrics at the end of the process. So this is a circuit equivalent representation of the dynamics we wanted to describe. Now, the memory is bounded by the number of levels in the environment, and it can be compressed. Okay, and there are some nice works here about compressing environment and so on. Okay, so in our theoretical work, what did we do? How did we test? How did we prepare the data and test whether we can learn these processes? Okay, so we consider one spin, which is our system, and three other spins, which are our environment, and we also couple these three other spins to some other super environment to change the memory, how much memory the environment has. And so we have locally just a sigma z system. Then the system is coupled to all the sites in the environment, all three of them. And then in the environment, we put some kind of XXZ model to couple them. We could have used other things. It's just an example. And as I said, the environment spins are also coupled to some local buffs, which tend to reset them with different velocity, and reset them at different states depending on the parameters gamma, which is the dissipation rate, and R, which tries to set the population in the state. So in principle, if just the environment were the super environment were acting on the three environment qubits, it will drive them to this mixed state, and but everything is connected, so this data will not happen unless for specific values of the Hamiltonian parameters. Okay, so now what do we want to learn? We have a process tensor which, given a certain set of preparations, gives the outputs. And we want to understand, for example, we want to see whether we can learn the final density matrix of the system, which is y at the last time step n, final n, the overall output, all the different outputs, measurements, and the process tensor itself, the MPO. We want to learn all of these things and see how well we can reproduce them and how this depends on the parameters of the tensor network that we use. Okay, one thing that we notice though is as we use the MPO to predict the final, the different steps, and specifically the last one, we find that these reduced density metrics are not physical, and this just comes from imprecisions. But what to represent them, we use a density matrix which is the closest to the local physical density matrix, which is closest to the one that we predict, and this will be really our prediction. Okay. The first quantities that I want to show you that we described are the infidelity. What is the infidelity? Is 1 minus the fidelity of the states, and particularly the final state that of the system, or of all the different ones, and then we average over them. Okay, so this infidelity here is the average over the different time steps output of the infidelity of the different outputs. Okay, so now let's look at the infidelity versus the bond dimension of our tensor network for different parameters. Gamma equals to 0 means that the superbuf is not resetting the environment, and so the environment actually has a significant memory. And in this case, the infidelity of our preparation is a bit high, 10 to the minus 2. It decreases as I increase the bond dimension, but it doesn't decrease significantly. If I put some resetting in the buff and I reset fast enough, I can significantly improve on our prediction, because the infidelity goes down significantly. And after a while, it doesn't even matter to change much the bond dimension. You get to very small values, which are bounded basically by the number of training data that we use. We can also play with the system buff coupling. Maybe I go back a moment. I remind you where it is. Is this coupling here between our system spin, and which is here, and the environment ones. And the stronger coupling, j equals to 4, makes the prediction much harder. Okay, but still we can see that the infidelity goes down as we increase the bond dimension, so our ability to predict improves as we increase the bond dimension. And later on, we can also try to see how this depends on the bond dimension and on the training data. So if I have a very small bond dimension, d equals to 1, basically I assume that the buff has no memory at all. The infidelity is not fantastic. Okay, and even if I increase the number of training data, it does not improve, because this is basically the expressibility of my network is not good enough. But as I increase the bond dimension, I can express, I can describe processes much more accurately, and even in increasing the number of training data, I can still improve. Some intermediate level, I could do like d equals to 4. I can improve significantly on d equals to 1, but eventually, after a while, even increase the number of training data will not improve the performance. So to improve the performance, we need to play both with the number of training data and with the expressibility of the neural network, of course. Okay, and the last quantitative slide that I have, we can try to describe all of the outputs and the variance, or how well I describe all of the outputs, or describe just the process tensor itself. And here I can see as a function of bond dimension and as a function of training data. And the key message here is twofold. Increase in bond dimension can improve significantly on our predictions, but only yes, but only up to a certain time, because after that you can go into some kind of overfitting. And to improve on this, you need more and more training data. You see, so training data more training data as you go down the slope here will allow you to avoid issues of overfitting that here starts already here, and then you can push it later. Okay. So now I go to the conclusions. MPS and MPO approaches seem to carry some potential, and specifically there are problems where we know the solution is naturally expressed as an MPO, and so using an MPO and tensor networks can be the ideal tool to represent these systems. And we have shown applications on cellular automata, on discrete nonlinear maps, and on these quantum processes. And I didn't show to you, but we also did some classification tasks with MNIST. Now, the process tensor that I described just now allows you to represent generic dynamics of open systems and consider both measurements and preparations. And this, since it can be described as an MPO, we can learn it effectively and actually efficiently as well. And the larger the memory in the buffer, the larger is the bond dimension that you require. Hence, the bond dimension is some kind of indicator of non-Markovianity, although the exact relationship between this bond dimension and non-Markovianity, it's a difficult task to figure out. But there are some nice works by Go-Chu on this task. Now, outlook. What are the best application of MPO for machine learning? Here we describe two, which seems quite natural, but there may be others. And of course, what are the limits of neural networks and the study of neural networks and many-body physics? And then also quantum neural networks, whether this can help. And of course, it would be great if there could be experiment with a true quantum system where the data is not given by our simulations, but by maybe quantum computer or quantum processing unit. And this could help this whole discipline to develop even more. It would be quite nice. And so with this, I thank my group and especially the collaborators in these two projects that I discussed, which are Go-Chu, Alanzie, Weilu, and Kawamodi. And thank you for listening.
Thank you, Professor Poletti, for this wonderful presentation. Let us thank our speaker. And we have time for questions. Yes, Dung, please go ahead.
Hi, sorry, I maybe asked some stupid question, but in my intuition, you can replace a tensor network with a deep enough quantum circuits. So are you sure that your model cannot be replaced by a deep enough neural network?
Oh, I never said it cannot. My question is whether it would be okay. So there are two questions. One is which one performs better, and by better we can talk about the fidelity of the output or the speed at which it performs. That's one question. The other question is about interpretability. So, and this is something that I haven't discussed yet. We know a lot about tensor networks. We know a lot about when they work and when they don't work because we've used them for decades on various physical models. And so this helps us to interpret some of the results. When we see something that works or something that doesn't work, it gives us a perspective of, oh, this doesn't work because the system can be thought about like that one with a certain type of long-range correlation or this type of couplings, which at the moment we don't have yet for neural networks, but maybe as we use more neural networks to study many-body physics, we may develop an intuition for that too. But at the moment, this intuition comes better from tensor networks.
Yes, so basically the point that I want to say is that in the neural network, you do not have the interaction between the node in one layer, but if you and I think that your your tensor network has this property because you have the interaction between two matrix, two nearest matrix. So basically, my point is that if you increase the number of layers, you can mimic this behavior of the matrix product in the new neural network. Deep layer neural network can mimic this this matrix product operator that you have.
Yes. As I said, in principle, you can use other type of neural networks. The question is whether you should and how or where the performance are. There are other advantages of using linear networks that I haven't mentioned also. For example, in our learning process, the cost function, the loss function always goes down monotonously. Yeah. While in neural networks, you may have to sample, and then since it's non-linear, it doesn't always monotonously go down. It fluctuates more, so there are other issues. But in principle, you can use them, and they can perform also well. The question is which one is better, and which one is easier to interpret. And even, for example, the discussion of non-Markovianity is not straightforward here to link the bond dimension to non-Markovianity, but it's definitely easier than if you have a complex deep neural network.
Okay, that's true. Thank you.
I think we lost Dylan, so I take the control of the situation. Are there any other questions from the audience? Apparently, I will say no. Okay, Dylan, you are back.
Yes, I had unstable network. I apologize for that. So any other questions from the audience? Seems not. So in this case, let us thank Professor Poletti again. And thank you all for joining. With this, we conclude our